Okay, so in the last video we have seen that the traction vector on the faces of a cube are represented in terms of a stress tensor. A stress tensor has two indices. Represents the first index represents the direction of the normal vector to the area, and the second index represents the direction of the force. So now we are interested in knowing how to represent a force acting on an area in any arbitrary direction in terms of the stress tensor components. So before we proceed, if we consider a mass of fluid, a given mass of fluid, or any object for that matter, we can have two kinds of forces. The first one is body force, second one is surface force. So body forces act throughout the bulk of the body, while surface forces are acting only on the aerial element of the body. So if we represent body force density as B, where B is body force per unit mass. So if we have acceleration due to gravity, we all know that the force is mass into gravitation. So the body force per unit mass in this case will give B vector is equal to G vector. Okay, it's like this. So if we are given that the body force per unit mass is small b, the components of B are B1 in the x direction, B2 in the y direction, B3 in the z direction. So for this particular term, if we want to find out the total body force, we have integral of B dm over the entire mass. So this is equal to integral B into rho into dV, integration over the volume. So where dV is the elemental volume of the total mass. Okay, so this defines the body force. Similarly, the surface force has been defined already. So these things, the traction vectors on the faces define the surface forces. Okay, and we have seen that if we have generalized orthogonal coordinates, we can represent the state of stress on a face in terms of the stress vector. Okay, so let us first do a 2D calculation. So let us consider the 3D problem where we have a prism like this. Okay, so if we have a prism like this, x, y and z, let us consider that the depth in the z direction is 1. So if we look at this prism from this angle, we have a figure like this. Let's call this as L3, L1 and L2, and let this angle be theta. Okay, so this is the side view of the same diagram. Now, what are the states of stress for such a prism? Let us represent the normal vectors first. So this is the normal vector, this is the normal vector, and this is the normal vector. So all these faces are oriented along these directions. So as we have seen in the earlier video, we can define the state of stress based on the traction vectors. So have a look into the earlier video. So here we can write this as tau 22. Rather, let's rationalize this. So this will be tau 11 because it's the stress acting on an element oriented in the x direction, because this direction is x and this direction is y. So this is tau 11. Okay, 1 represents the direction of the normal vector and this one represents the direction of the force. Similarly, this will be tau 12, this will be tau 2 2, this will be tau 2 1. If this is n, if we have any arbitrary force acting on this F, so we recall that the traction vector acting on a face oriented along n has the components tn1, tn2, tn3. But because we are in 2 dimensions, we disregard this. So we have only the 2 components. Okay, so if we recall, the traction vector is the limit delta A tends to 0 F vector divided by delta A. So traction vector multiplied by dA gives you the force. So what will be the area of the top face? It will be 1 multiplied by L3. Because this length is L3 and the width into the plane of the paper is 1. So this is L3. So L3 multiplied by 1 gives you the area of the top face. Similarly L1, if this is L1, L1 multiplied by 1 gives you the base area, and L2 multiplied by the depth gives you the face area of the length L2. So area of the top face is L3 into 1, which is simply equal to L3. Similarly area of left face is L2 into 1 equal to L2, and the area of the bottom face is equal to L1. So let us write down a force balance. Summation of all the forces is equal to mass into acceleration of this element. So if we have summation of forces in the x direction is equal to mass into acceleration in the x direction, because the acceleration has the components a1, a2 and a3. So the force acting in the x direction is first of all T1n multiplied by the area. So T1n multiplied by L3 minus this contribution minus tau 11 multiplied by L2 and minus this component minus tau 21 multiplied by L1 plus a body force. So the body force is equal to the volume. So what is the volume? Volume is equal to area multiplied by the width. The width into the plane is equal to 1 and the area is half L2 into L1. So this is half L2 L1 into rho into B1. So we recall that the body force is equal to the mass of the system. So this thing becomes the mass because it is density multiplied by the volume times B1. B1 is the volume force per unit mass. So this should be equal to half L1 L2 rho into A1, mass into acceleration. Okay. Let's divide everything by L3. So we have T1n minus tau 11 L2 by L3 minus tau 21 L1 by L3 is equal to half L1 L2 by L3 rho A1 minus half L1 L2 by L3 rho B1. We let the volume of the element go to 0. So here comes the important concept that even if the lengths are tending to 0, the ratios of the lengths do not go to 0. In fact, the shrinking is taking place in a very proportionate manner, so that even if the lengths are going to 0, the ratios are fixed. That is to say, the angles between the three sides are fixed. Okay. So if we let the lengths go to 0, this thing is constant, this thing is constant. Because this thing is constant and this goes to 0, so this thing is constant by this logic, but L1 is going to 0, so this whole term becomes 0 and this whole term also becomes 0 by the same logic. Therefore we have T1n equal to tau 11 L2 by L3 plus tau 21 L1 by L3. Okay. Similarly, let's do the balance in the y direction. In the y direction we have Tn2 multiplied by L3 is equal to T22 multiplied by L1 plus T12 multiplied by L2. We have discarded the volumetric terms because as the volume goes to 0, those become neglected. So T2n is equal to tau 12 L2 by L3 plus tau 22 L1 by L3. From geometry, we know that L1 by L3 is equal to cos theta, and L2 by L3 is equal to sin theta. So if we want to express these thetas in terms of the angles between the normals, because we have already seen that we can define an area in terms of the face normal. Okay. So if we have one line like this and another line like this, what is the angle between the two lines? We have two vectors A and B. A dot B is equal to mod A mod B cos theta. So the angle between them is this. Okay. But we see from geometry that the angle between the two lines is the same as the angle between the two normals. If I bring this angle here, it will become something like this. So this theta and this theta become the same. So I call this AB and this is CD. So this is AB and this is CD. So the angle between the two lines and the angle between the two normals to those lines are the same. So similarly over here, in this particular case, we have this and we have this. So this theta is the same as the angle between the two normals. So the normal to the horizontal line is in the j direction. So the n vector for this line is j cap. So the normal vector for this line is j cap. Similarly, the normal vector for this face is n. We have already defined it as being n. So if I translate this over here, we see that this angle and this angle are the same. So cos theta is essentially n vector dot j, and sin theta is similarly n vector dot I, because this direction is I. So if I can flip and superpose this over here, sin theta is essentially cos of this angle. So this is the angle between n and I. So it becomes sin theta. If this is cos theta, this is sin theta. Okay, as easy as that. So good. So cos theta. So we have found that this L1 by L3 is equal to n dot j, and L2 by L3 is equal to n dot I. So this is equal to, so what is n dot j? So the components of n are n1 and n2, and n dot j is a dot product of this with 0, 1. So it's only n2. Similarly, n dot I is simply equal to n1 n2 dot product with 1, 0. This is simply n1. So L1 by L3 is n2 and L2 by L3 is n1. So we obtain the following relationships. Tn1 is equal to what? tau 11 L2 by L3 plus tau 21 L1 by L3. So L2 by L3 is N1. So tau 11 N1 plus tau 21 N2. And similarly, T N2 is equal to tau 12 N1 plus tau 22 N2. We have used this in this equation. So this gives us the state of stress as the traction vector acting on a face with an arbitrary orientation. Okay. So thus we have obtained the traction vector on a face oriented in the direction n, where n has the components n1 and n2, tau 11 and so on are the components of the stress tensor. So essentially we have represented the force acting on the face. So how do we find the force acting on the face? So we recall the definition of the traction vector. So the traction vector is limit delta A tends to 0 force by area. So now the force is simply the traction vector multiplied by the area. So dF will be simply the dA. Okay. So you just multiply this by the area to find the force. So this is the force acting on a face oriented along n, having the state of stress tau 11, tau 21, tau 12 and tau 22. Note that F and N need not be oriented. They can have any random orientation as well. Okay, so let's see how we can do a small example. Okay, let's consider a state of stress. Okay, before doing this example, let's just see how we can represent this equation in a matrix form. So if I write down the two components of the traction vector like this is equal to some matrix multiplied by n1 n2. So what are these? So this will be tau 11, tau 21, tau 12, tau 22. So if we multiply this, we can obtain a direct computation of all the components. It's convenient to do this in a computer, but let's see. So if we are given that the stress tensor, so this entity is the stress tensor. Okay, so if we are given that the stress tensor, the tensor is marked by a double bar on the top, is equal to 0 a 0, and so we want to find out what is the force on a face oriented at 30 degrees to the horizontal. So the face is oriented like this. So the n vector is what? So it is oriented at 30 degrees. So if this is 30 degree, this is 30 degree. Okay. So what is n vector? N vector in this case will be sin 30 I, and it will be cos 30 j, because the component of this is found out using this simple trigonometric rule. So sin 30 is half, so forget this I and j because we have already written them in the bracket notation. So this is the I component and this is the j component. So essentially it's half and square root of 3 by 2. So now what is the state of stress? So the traction vector t and 2 is thus equal to 0a 0 multiplied by half and square root of 3 by 2. What is this multiplication? This multiplied by this plus this multiplied by this. So this is equal to a into square root of 3 by 2. Similarly, a into half plus 0 into 3 by 2, a into half. Okay. So the force in this particular example has this orientation. So the normal was oriented at 30 degrees. So the normal was 30 degree. So what is the angle? Okay, so we know that the x component of force is square root by 3 by 2a and the y component of the force is a by 2. So what is this angle? So this is also a by 2. So sin theta in this case becomes half. So sin 30 is half. So this angle again becomes 30 degree. So F is at an angle 30 degree from the horizontal. So this theta becomes 30 degree. So clearly the force and the normal vector are not oriented. So this is 30 degree because sin 30 is half. So if this is a by 2 and this is through square root of 3 by a, this is automatically a from trigonometry. Okay. So the final figure would look something like this. If this is the area, this is the normal vector, and this is the force. The force and the normal vector are not oriented along each other, as we have already noticed. Okay, so this example clearly shows how to find out the traction vector. So how do we find out the force? So we have already found out the traction vector is equal to square root of 3 by 2a and half a. So the force is equal to square root of 3 by a into area half a into area. As simple as that. So in the next video we will try to do an example of 3 dimensions. We will first do the derivation and then we will see 3-dimensional example.